Okay, so welcome back to the theory of probability. So let's quickly review what we did in our last class. So we discussed several things. We discussed the theory of continuous time random variables. We discussed two particular very important examples of the continuous time random variable, that is uniform random variable and the normal random variable. I would like to quickly recall some of the basics of the normal distribution because that's what we're going to begin today. So you remember that we're going to say that x is normally distributed with the parameters mu and sigma square if the PDF of this normal distribution can be written as x minus mu by sigma square and everything divided by 2, okay, and everything divided by 2 pi and sigma outside. So this is what the PDF of this is. In particular, if mu is 1, if mu is 0 and sigma is 1, then that is, if x is normally distributed with mean 0 and variance 1, then x is called standard normal. Okay, so this is what that we also discussed actually, that it's called a standard normal. And then we talked about some of the basic properties, the relationship between the non-standard normal and standard normal, a general random variable and a standard normal. So we said that if x is any for a standard normal, we're going to use mostly the symbol z. So some of the properties that we discussed, important properties that we discussed, were that if x is a normally distributed random variable with mean mu and variance sigma square, then if you subtract mu from it and divide it by the standard deviation, then this new random variable, which we call the standardization of the non-standard normal random variable, is basically a standard normal random variable actually. So if you subtract x from mu from the general random variable and divide by square root of the sigma square, the standard deviation, you're going to get a standard normal random variable. And then we talked about some of the basic properties of the CDF of the normal random variable. I mean, if you remember, the CDF of the normal random variable goes like this. Okay, so it's minus infinity to x and e to the minus x square by 2 and everything divided by square root of 2 pi and dx. Okay, so we can't solve this integral analytically, so we saw that for the values of x, okay, for the different values of x, we have a table actually. Okay, so this has been solved numerically. Okay, and using that table, we can compute the different values of the phi actually. And another important property of the standard normal random variable was that if you want to compute say phi of minus z, you can compute it by complementing phi of z. And this holds because of the symmetry of the bell curve. I mean, if you for example plot this curve, the plot would be a symmetric bell curve actually. Line vector is not symmetric, but yes, we may assume that it's symmetric, a bell curve. So these are some of the things that we discussed in very detail last time. We did a lot of calculations and computations. So what I would like to do today, I would like to talk some examples of the normal random variable or the normal distribution, and some more properties of some more interesting properties of the normal distribution, and then I would like to move to some other interesting distributions, which are the examples of the continuous time random variables. Okay, so here is the first example that I would like to do. So this is the example for phi from the Ross, Sheldon and Ross, the first course in probability theory. And this example is about basically what you call it's so-called the grading on the curve actually. Grading on the curve. Rather, it's it's a technique that you usually use when you are trying to do the relative curve actually. So the question is, imagine you want to take an exam, okay, and then so you have the exams and you have the exam results with you, and now what you want to do, you want to have a kind of a good examination strategy, a marking strategy for that examination actually. So the question is how the grades should be distributed among the students so that we can call that grading strategy as a fair grading strategy or a good grading strategy. So the one way of doing it is to basically approximate your grading strategy should give you a normal curve of the grades actually. Okay, so imagine you have test scores. So you have exam scores. How to work on that strategy. So you took exams and you have exam scores with you. You have the numbers actually. Someone got 30 marks. So say imagine it was a 50-mark exam. Okay, some got 30 marks, some got 48 marks, some got maybe 10 marks, and some got 20 marks, and so on and so forth. Now you want to set up a criteria. Okay, you want to assign say grade A, but you want to know that okay, at what score I must give grade A, or at what score I must give grades B or grade C, or at what score I must say for example fail the student actually that okay they haven't passed the exam. So you have the exam scores with you, you have the numbers with you. So using that exam score, you can obviously compute say average of the exam score easily. Okay, so that's not a big deal. So what you need to do, just sum them up and divide by the total number of scores actually. And you can also compute the variance of those exam scores. Okay, so you have test scores, and from that test scores you fetch the average and say the variance of the average and the standard deviation of the exam scores. Now you want to do the grading on the curve. So what can be done? So ideally what you can do is that you can assign grade A to those students who have marked mu plus sigma. Okay, so assign. So if X say represents the marks obtained by a random student, then you're gonna say that okay, let's assign grade A to those students which have marks bigger than mu plus sigma actually. So those who have marked more than mu plus sigma, let's assign say grade A to those actually. Let's assign say grade B to those. Okay. So who will take the grade B? Assign grade B to those who have marks in the interval say mu to mu plus sigma. Okay, so those who have marks here in this interval, let's assign say grade B to those actually, and grade C to those students who have, say, marks between, say, mu minus sigma to mu. Okay, so let's call this out. And let's assign grade B to those who have marked between, say, mu, say, from mu minus sigma, mu minus 2 sigma to mu minus sigma. Okay, so we have a score between mu minus 2 sigma to mu minus sigma. Let's assign grade B to those. And those students would fail, if they are getting a mark less than mu minus 2 sigma. Okay? Mu minus 2 sigma. So if x is here, here, so let me say it again. So you took an exams, you have exams on scores with you. You want to do a grading on the curve. In other words, grading through the normal distribution, or that approximates normal distribution, because that's what usually is termed as the fair grading strategy. Then on what score you should assign, say, grade A to the students, and on what score you should assign, say, grade B to students, and grade C and D, and fail. So assign all those students who have more marks than mu plus sigma, the grade A, and grade B to those students who have the marks between this interval, and so on and so forth, actually. Okay? So this should be the grading strategy. So that's really the grading strategy for any marks. I mean, normally when in many of the places, so when, for example, the different grading policies are being set, like this is one of the, what do you call, the guiding principle actually on which the grading policies most of the times are made. Not necessarily always, but yes, most of the time. Here's an interesting question. Imagine you are a student, okay? Have a student, a particular student, whose score is X. Now, what is the probability that this student whose score is X will get an A grade actually? So we know that it will get an A grade if X is mu plus, it has a more score than mu plus sigma. Obviously, we can assume that with this strategy, X would be a normally distributed, or it can be approximated by a normally distributed random variable with the mean mu and variance sigma square actually. Okay, so what would be the probability that a student would get an A grade actually? Or you can also say that, okay, what percentage of the students will get or should get A grade in a fair kind of examination system. So what we should do, if you want to compute this probability, the guiding principle the same, that you standardize it and then compute the probability. So how can I standardize it? So for standardizing it, I need to subtract a mu from X and divide by sigma. So when I'm going to get this, I'm going to get a 1 here, obviously. So you take this mu on the other side and divide by sigma, so you're going to get a 1. So that's in a standard normal random variable. That means that you should have a phi of 1. So this probability is really phi of 1. So the phi of 1, when you're going to look it from the table, is going to be approximately 0.15 87. Okay, so around 16%. So there are 16% chances that a random student will get an A grade, or at least, so another interpretation of like this could be that, okay, at least the 16% of the student should get A grade actually. Okay, in under normal circumstances. How about those who get the B grade? So mu to mu plus sigma, say. We can also simplify this by subtracting by mu and dividing by what do we call sigma. So I'm going to get x minus mu by sigma between 0 and 1. Okay, and this probability can be computed by computing the phi of 1 minus what do we call the phi of 0. And this can be approximated by 0.31 3413. So around 34% of student, there is 34% of a chance that a random student would get a grade B. So similarly, we can make a computation of all other possibilities. So say between between say mu minus sigma to mu. So you can compute this probability, and it turns out that this is also this is also 0.3413. You can use the same principle, but what you're going to get is 5 0 minus 5 negative 1 actually. Okay, and how many of what is the probability that a student, particular student with this grading strategy would get a D grade is really mu minus 2 sigma and mu minus sigma. So it's going to be phi of 2 minus phi of 1 on simplification. So you're going to get, what do you call? So you're going to get a number that goes like 0.31, not 0.31, but 0.1359 actually. So around 14% would get a D grade actually. While a random person, so a random student, so what is the probability that he will fail the exam? So we need to compute the probability of this being between mu minus sigma and x being less than mu minus 2 sigma, okay, and this can be computed as basically, so dividing by subtracting by mu and dividing by sigma would give me phi of negative 2, and this number is really 0.0228 actually. So around 2% student will, so there is a 2% chance that you would fail the exam actually. Okay, so this grading strategy based on the normal distribution is called the grading on the curve actually. So when you are, for example, taking your test or taking your exams while you are teaching in your schools and colleges, you can adopt this strategy. Okay, so take exams, scores, assume. Not assume, but compute mu and sigma squares for your exam scores, and then assign the grades according to this policy. So you're going to get a grading. So you will have a grading curve, or you'll get a what do you call a beautiful bell curve of your scores. So this is what is the key thing. So that's one of the examples. Let's move to another interesting example that is going to show that how normal distribution can kind of help us dealing with different kind of practical situations. Okay.